Welcome to part 3 of the nuclear physics videos. In this video we're going to be taking a look at the overall nuclear reactions and nuclear decay. And I'm going to be using these two images that are from the openstacks.org website. I have a link in the description below. Excuse me. Now what we have here is a radioactive source. And in the mid to late 1800s and the early 1900s, scientists, chemists, and physicists particularly started to study other kinds of matter because we were trying to understand how subatomic particles behaved. And what they started to notice was that if these elements, these radioactive source elements, were left in near or in the presence of a magnetic field and in a cloud chamber, that inside the cloud chamber or a bubble chamber, we would see streaks or contrails, kind of like you would see for an airplane leaving behind traces of the motion or the trajectory that it took. And we know from our study of electromagnetism that based on the direction of the curve of the path, there is a certain charge associated with the particle that made the path. So we know that from the equation F sub m, or F sub b equals qv cross b, we know that this represents the amount of magnetic force that's acting on a charged moving particle. So if we see a particle had an initial velocity to the right here as it entered the magnetic field and it curved upwards like this, it would imply that there has to be a force pointing perpendicular in the direction of the turn to the velocity. Now if we use the right hand rule to backtrack to figure out what charge this has to have, we have our fingers representing the magnetic field pointing into the plane of the page, the index finger, the velocity pointing to the right, and that does leave my thumb pointing up in the direction I would expect the magnetic force to be. So that leaves this as a positive particle because it does follow the constraints of the right hand rule. Now, if we take a look at the bottom one here, because it's turning exactly the opposite direction to this top one, it implies that it must be a negative charge because it turned in the complete opposite direction. And if we were to use our left hand with our fingers oriented in the magnetic field direction, our index finger oriented in the initial velocity trajectory, we would see that in fact the magnetic force would point down. Now, from the amount of curvature over here, we can see that if the same force is being applied to these because their magnitude of charge is the same, the mass would affect how much of a turn each of these things would make. And we would be able to see here that this negatively charged particle has a less mass, and the positively charged particle would therefore have more mass than that. Now, in order for a particle to be undeflected in a magnetic field, that would imply that it has no charge, because we know it has initial velocity. We can see the contrail that it makes, and there's no electric field here to balance out this particle. So this one over here in the middle must have no charge. So if we take a look at the kinds of particles that come off of radioactive sources, what we found through a lot of experimentation over many years is that these positive, more massive decaying particles are known as alpha particles. These alpha particles don't have as much energy as some of the other kinds that are being emitted, and so in this image here you can see it visualizes very well the fact that a sheet of paper would be able to stop an alpha decay particle from continuing motion. Now the less massive over here at the bottom is known as the beta particle. And the beta particle is actually going to come in two different forms. We have positive beta particles, and we also have negative beta particles. The negative beta particle is the more or the first discovered one, and this is essentially an electron-like particle, or an actual electron. The positive form of this same electron is known as a positron, sometimes called an anti-electron. Now these beta particles have a bit more energy than the alpha particles, and it would actually take some metal to stop them moving. So maybe several sheets of aluminum foil or a copper plate or something like that to stop the beta particles from moving. Now the last form over here actually showed not only to have no charge, but also to have no mass. And this strange particle is said to be called a gamma ray, or a gamma radiation. And this is a very high energy form of radiation. It can actually pass through paper, metal, even thick concrete, and is really only stopped by thick lead. And so all three of these different forms can occur at the same time, can occur at different times, and what ends up happening is that we see that an unstable nucleus, which consists of nucleons, protons, and electrons, will break apart, releasing one of these particles. Let's just use the alpha particle as an example. And the result will be that if you've lost an alpha particle, you're actually going to form a new element. So not only are these radioactive sources naturally emitting particles that can be detected through different forms of radiation, they're also forming a new element in the same radioactive process. And over the next few videos, we're going to take a look at how alpha decay occurs, how beta decay occurs, and then how gamma decay occurs.